Is this better? Is this better? Hello? Yeah, cool. Right. So the speakers of this talk literally need no introduction, and it's very difficult to introduce someone who needs no introduction. So I would like to give this difficult task to my co-convener Simar. And yeah, so after a short introduction, we'll get started with unpacking the Muon g-2.
Hello all. As Vito said, the speakers don't need any introduction. Still, I have written a few words about them. So, Professor Anand is a professor here at Center for High Energy Physics. He has served as the chairman of the department. He completed his bachelor's from IIT Madras and then his master's and PhD from University of Delaware, US. His research spans low energy physics at high precision and physics beyond standard model, and he has made important contributions to both theory and outreach. He will be delivering the main part of the talk today, and it will be followed by a talk by Leonard. Leonard here is a PhD student at Center for Energy Physics under Professor Justin David. His research focuses on holography and physics beyond the standard model. So with this, I would like to give the mic to Professor Anand.
Just one minor correction, mine is not the main part, these are equally important parts. Okay? So today I'll have the pleasure of talking to you about this topic, which I've entitled Unpacking the Muon g-2. The muon is an elementary particle which is about 210 times the mass of the electron. Okay? It is the longest length of all of these unstable elementary particles, and we need to have a scale in this problem what we mean by long lived. Its lifetime in its rest frame is about 2 microseconds. Okay? So how many of you here have heard of the LHC, Large Hadron Collider? So it has many important experiments, one of which is called the compact muon solenoid. Okay? So you see the word muon over there. So one of the many uses of the muon is that since it's very long lived, it can traverse long distances and deposit its energy. So even in an experiment like the LHC, the muon plays a very important role. It is produced, in these collisions of very energetic particles, then travels a long distance, and then you can track it very well and look at its energy deposition and all these things. Very nicely. So that's one part of this title. And what's the other part of this title? I think is there a pointer in there? Pointer? It doesn't matter. Okay. So the other part of this title is g-2. Now, how many of you here have any idea what this g-2 stands for? Doesn't matter if you don't know, because I hope that at the end of this hour and a half you will know what the g-2 is. Any idea what this g-2 is? So it is related to the anomalous magnetic moment of the muon. Okay? So it's a fundamental property of this particle, and we write it as g-2 because if it is a truly elementary particle and it's described classically by the Dirac equation, which describes spin half particles, as a classical theory, its value would be equal to 2. Okay? So when you say it's g-2, it means it's deviations from this expected value of 2 because of quantum corrections. This is also very nice because this is the year of the quantum. Next week I'll be talking in Chennai about the same thing. There's a whole 1-week conference on celebrating the quantum. So the g-2 here represents the corrections, if you will. It's not a correction, but it's like quantum contributions to the magnetic moment of the muon, and it's called the anomalous magnetic moment of the muon. Okay? So this is what we are after in this talk. Yeah. So what is a muon? So this is too small for you to look at. So it says that this is the marvelous muon, and I myself can't really read it, but I'll tell you a few words about this. So this is an elementary particle that was discovered, I think, in about 1935 or so. So that was a time when we knew how to model the nucleus in terms of nucleons. there are two species of nucleons, namely the proton and the neutron. Okay? So, how does the nucleus form? It's because of attractive forces of the nucleons. And then Yukawa had a theory where he said that, look, there must be a force carrier which is responsible for binding this. Okay? So when the muon was discovered, they thought that this is the force carrier, and it turned out that it was not. The actual force carrier is called the pion, which was discovered much later, in 1947 or so. So this muon, when it was discovered by Anderson and Nedemayer, Ravi is supposed to be very upset and said, who ordered this muon anyway? So the pion on the one hand is a particle which participates in the nucleon force, participates in strong interactions, whereas the muon is exactly like the electron, except that it is 210 times as massive as the electron. Okay? So, like the electron, it does not participate in the strong interactions, it only participates in weak interactions, and it participates in the electromagnetic interactions. So, it belongs to a family of particles that are known as leptons. That's the name to begin. For every electron, there is a neutrino. For the muon, there is a muon type neutrino. So, the muon is an unstable particle, as I said already. It decays with a lifetime of 2 microseconds, and it decays into what? What can it possibly decay into? It can only decay into particles that are lighter than itself, right? So, apart from the electron, which is a charged particle, it has to decay into something else, because no particle can decay into a single particle, because you cannot observe energy and momentum. It has to at least decay into 2 particles or 3 particles. So you may say, why doesn't the muon decay into an electron and a photon? There's nothing wrong with that, except that it's not been observed. The muon decays into an electron and 2 neutrinos, one of the muon type, one of the electron. So it's a 3-body final state where the muon decays into an electron. Not only does it decay, but it decays in a very specific way. This is called a weak decay. It's just a historical name. Don't think of these names, strong, weak, as being, very muscular, this, that, and the other. These are just names. Okay? Like you have the electromagnetic interaction, you have the weak interaction, the strong interaction, you have the gravitational interaction. Of course, all these participate in the gravitational force. Everything that we know participates in gravitational interactions. Anyway. So the muon decays into an electron through the weak interaction, but this weak interaction has a very special property, and it violates parity. What is parity? Parity. So it's the invariance of laws of the physical world under reflection through a mirror. Okay? That's called parity. So if you reflect something and reflect it back, it's as good as not having done anything at all. So today we know the structure of the interaction that leads to the decay of the muon. It's a parity violating weak interaction, all of which is very important for this particular experiment. Every single word that I have mentioned so far is important in the design of this experiment and in the measurement of this basic property of the muon, which is the anomalous magnetic. Okay. Now stop me if there are any questions. Okay, so everything that I have said is captured in the slide. So the muon is an elementary particle, and it's like the electron in all respects, except it's about 210 times heavier. And it decays via a weak interaction, which is called a charged current interaction, into an electron and a pair of neutrinos with a lifetime of approximately 2 microseconds in its rest frame. So I'm constantly talking about the rest frame over here. Why is that? Because in the experiment that we will do today, the muon is highly relativistic. Okay? So what happens if a particle has a certain lifetime in its rest frame and is highly accelerated in the laboratory frame? What do you expect will happen to its lifetime? When the clock is in the laboratory frame, obviously, right? So what do you think will happen? It will be much longer, which is very good for us, right? In fact, it would be, I would say, about 800 times. Just don't take all these numbers literally. These are things that you have to go back and check for yourself. Okay? How much longer is it? I didn't check this morning, but I've already forgotten. What's the factor by which the lifetime increases? And this thing is going to go round and round in a ring that we are going to design today. When it goes round and round, obviously, you want it to go around large number of times so that you can do experiments with it before it eventually decays. And how will it decay? What's the kind of radiation, what's the kind of law that you expect when particles decay through radioactivity? What kind of lifetime do you expect? It has a half-life, right? So you see, if you have a beam of particles and you expect that the population of the particles decays exponentially. So these are again the basic physics principles that you will be using in designing this experiment. So this radiation law that you know, radioactivity, as well as the enhancing of the lifetime from its value and the rest going into it in the laboratory frame, because it's a highly relativistic beam of particles that can be used. So these are all the properties that I said already, so I don't have to show it again here. So the magnetic moment is associated with just the interaction of this muon over here with the photon line like this. It could be an external photon line like this. And in this vertex over here, you have two contributions. One is the electric charge itself, and other is the magnetic moment, which you can obtain in the non-relativistic limit of the Dirac equation. There's a well-known procedure by which you can read off the magnetic moment of a charged particle by treating the Dirac equation appropriately. Now, if you didn't have all this stuff in the bottom, then the g minus 2 of the muon would be 0. G would be equal to 2. But all this gets corrected by the fact that we don't live in the classical world, but we live in a quantum mechanical world where it is possible, quantum mechanical as well as a relativistic world, where it's possible to have the production of virtual particles in the vacuum so that the charged particle that you have, namely the muon, is sensitive to the activity of the vacuum itself. So that's where the G minus 2 is coming from. This blob over here, which is going to yield for you the G minus 2 or the muon. But how do you measure this magnetic moment? Well, if you want to measure the magnetic moment, then it better be a magnetic field, right? So you take this particle which has a magnetic moment, and you have to immerse it in a magnetic field, hopefully a very uniform magnetic field, so that you can get an accurate measurement of its magnetic moment. So let us consider the xy plane, namely the plane of this table, and let us have the magnetic field coming out of the plane of this field, and then you have, let us say, the muon. Here it is called the mu plus, with its spin vector pointing in an arbitrary direction. And if you have a non-zero V, then this thing is going to precess around the. So this is the magnetic field, and this is the muon, which is spin half. And every particle that is spinning actually is like a tiny little magnet over there. Okay? So this magnet is going to precess around the magnetic field, like this. And you get the greatest precession, not when it is at some angle theta, but essentially when it is at pi by 2, that's when you will get the maximum magnetic field. Since this is also a charged particle, and if it is moving around, let us say, in a ring, where the ring also has a uniform magnetic field everywhere, then the principle of the cyclotron tells you that this muon is going to stay in a circular orbit, because the velocity, the cross product of the magnetic field, is going to give you a centrifugal force, which is going to keep it in a circular orbit also. Okay. So the precession of this guy in this field is also going to follow the centrifugal force. The vector over here is the head of the vector, is going to be the head of the centrifugal force vector also. As you move along this, it's the same thing that is going to go around. Okay? And if the G minus 2 is 0, then the precession frequency will actually be equal to the cyclotron frequency. Now, isn't that amazing? That it's very nice. It's just the properties of this Dirac particle, properties of the cyclotron principle, which tell you that if G is equal to 2, then the rate of precession is going to be exactly equal to the cyclotron frequency. Okay. Now you tell me, how do I measure the G minus 2 based on the few words that I've said earlier? How do you measure the G-2? Exactly. So this means that they are actually marching lockstep, the centrifugal force as well as the precession. If it was exactly equal to 2, then they would be locked in step. Okay? But because the G minus 2 is not equal to 0, it means that as time goes along, there is going to be an increasing angle between the centrifugal force.
Is this why the lifespan increasing at 650 micros that the angle can actually become large enough?
In a sense, yes, but that's not the real reason why you are going to have ultra-relativistic. There are many factors. So, what we will see in the later slides is that it is going to be an ultra-relativistic energy, but of a very important special value, which is called the magic energy, which was discovered already 50 or 60 years ago, to maximize the efficiency of the measurement. Yeah? And of course, it's 2 microseconds in the elementary particle physics world is a very large lifetime. Okay? So, yes, of course, it's very nice to enhance it by a factor 80 or 100 or whatever, and it helps a lot, but I don't know exactly how to answer your question, but these are all interrelated factors as far as the experiment is concerned. Okay, good. What about the experimental situation and what is the theoretical situation? Now, obviously, if you're saying that you're going to do a very precise experiment, then your theory gives you a precise value for the G minus 2, and then you want a very accurate measurement of the same G minus 2. And if the two things agree, then you say the theory and experiment are in agreement. And if they are not agreeing within errors, then you say that there's a discrepancy. Okay? And the amazing thing about this particular experiment is it's one of the most accurate measurements ever made of any physical quantity, which means that the theory also has to be of sufficiently great precision so that there can be a meaningful comparison between the two. Right? I can really see. Tired? Only as tired as me. But anyway, so that's what we're going to try to do. We're going to ask what is the level of precision and what is the level at which theoretical calculations are performed in quantum field theory. Now it's very easy to write down the vertex like this. This is an example of a Feynman diagram, but you have more and more complicated diagrams as more and more virtual processes in the vacuum are accounted for. Okay, so the simple blob over here may have a large number of honest to goodness Feynman integrals. This is just a schematic representation of the theoretical contributions to this. Okay. So, in the 1960s, which is a long time ago, as you know, at least as old as your speaker, these experiments were performed and there was a lot of uncertainty, and a very accurate experiment was conducted in a place called the Brookhaven National Laboratory. The name of the experiment is very these experiments have very boring names and numbers. P821 doesn't stand for anything except that it was E for experiment, and 821 must have been the number that some bureaucrats stamped on the proposal. And it was finished towards the end of the last century, and the early part of this century, the analysis of the data was done. And the successor to that experiment was conducted at a place called the Fermilab, and then the experiment was called the Muon G-2 experiment, which reduced the uncertainty by a factor of 4. And the reason for doing that was that the Brookhaven experiment gave a number which was not really in agreement with theory. There was a mismatch between the two. Any idea where this Brookhaven National Laboratory is? It's in the state of New York in the US, on the East Coast, in a place called Long Island. And this Fermilab is in the middle of the US. It's called the Midwest, in the state of Illinois. So why is this of interest or importance to us? Because the first experiment was done with a very large magnet, which was done in Brookhaven. And then it's not like you can build a new magnet every day, right? So if you stop the experiment, what do you do with that magnet? You have to move it to the other place. But this is an enormous magnet. This magnet is probably larger than this room. Okay? And you can't dismantle it and take pieces and so on. So what they did was they took this magnet and then they moved it through. There's a river which connects this place to the Atlantic Ocean. Went out into the Atlantic Ocean, and went all the way around and around Florida, and then what do you enter after Florida? When you go up north, it's the Gulf of Mexico, and then after the Gulf of Mexico, yes, this guy knows everything. There's a big river called the Mississippi River, and it went up the river quite a bit, and then there was a very large system of trucks on which they took this magnet and moved it, and then they had to reach the other place safely, install, testing, all these things. It took many years to do this. So, that's a kind of effort that goes into these things. And the principle of the experiment is this. So you have to produce muons. How do you produce muons? So obviously all the particles in elementary particle physics are produced in collisions of stable particles. Because what the special theory of relativity tells you is that you can take energy and turn it into matter. That's how it is different from non-relativistic physics. Right? In relativity, as Einstein said, which you could read on any t-shirt, E is mc squared. If you have enough of energy, you can turn it into particles. So you have a fixed target, and you hit it with some other particles, then it produces a large number of other particles without violating any conservation laws. It produces particles that are known as pions, that I mentioned earlier. And pions primarily decay into muons and neutrinos. Neutrinos are very weakly interacting and they escape. So these muons which are produced, you can collect them, collimate them and all that, and they purify your beam, and then use that beam to study muons. The reason why you can collimate them and so on, because these are electrically charged. So you can use electrical fields in order to focus these particles. Of course, there's a whole science, and this science is 70, 80, 90 years of experience that we know how to do all these things. By we, I don't mean we, but people in Fermilab know how to do it. So that's what you see over here. So you have protons. So this was for the Brookhaven experiment, AGS, which stands for, can you all read this? Yeah. Probably can't. Right? You didn't bring your binoculars into this? The guy in the back, there's a spot for you here. Where did you come in? All good. Otherwise, yeah, come up front. Okay, so here it is. It says AGS, which is the alternating gradient synchrotron, which hits a target, and then that produces pions. And the pion is about 20% heavier than the muon, and primarily decays into a muon and its neutrino. The question: why doesn't it decay into an electron and its neutrino? Electron is even nicer, even lighter. So wouldn't it like to decay into that? The reason again is parity violation. That the pions preferentially decay to the muon rather than the electron, which is fortuitous to us because we can do this experiment. Okay, so here are the pions which decay into muons, and then they are injected into this ring whose diameter is, as I said, 14 meters, right? So my guess was right. So that magnet is roughly the size of the room. Okay, 14 meters. You agree that this must be about 14 meters? No, it's probably not even 14 meters. What is it? The length may be about 14 meters. Right? Less. Anyway, so we have a rough order of magnitude of how big this magnet will be. So this thing over here, as you can see, it goes all the way around, and then you see a very nice depiction over here of this polarization vector that I mentioned. You can see the cone, the head of the cone is precessing. So you can see that the principle of the experiment is already shown over here. And then when this muon decays, then the daughters from that muon are two neutrinos and an electron. Of course, the neutrinos escape, and the only particle you detect is the electron. If it is a mu minus, or it will be a positron. If it is a mu plus, depending on which it's and how you do the experiment, whether you do it mu minus or mu plus. Right? And the other nice thing, again and again let me emphasize, that because this is a parity violating interaction, the charged particle, if it is very energetic, is strongly correlated to the direction of this polarization vector. It's really amazing that nature has provided all these, methods of doing an experiment like this. But this is not a high school experiment, where you take a pendulum and measure the G. It's not like that. It's like such a complicated thing where you have to use all the elementary particle physics that you knew in order to design this experiment. Right? So this figure already tells you essentially the principle of the experiment. That if you count sufficiently energetic electrons coming from this decay, then you have almost a direct measurement of this polarization of the muon, okay? Which, as you know, develops a mismatch with the direction of motion compared to the direction of polarization. That's the principle of this experiment. So, this here, the first treatment of the g-2 was done in a theory that we call quantum electrodynamics. So quantum electrodynamics, which means the dynamics of the electron and what? Unless there is a photon, there is no dynamics, right? If the photon is not there, then the electron is not interacting with anything, so there ain't no dynamics. So unless there is a proton, there is no question of. So this is one of the most pure theories imaginable. It has only two parameters, which are the mass of the electron and the charge. Nothing more. Okay? And everything else is a derived property from just these two parameters. But later, this has been extended to count for other charged particles, such as the muon, the quarks, as well as the tau electron, which is an even heavier present in these days. So this theory, you can say that there are two parameters, me and alpha, which is e squared by 4 pi, yes? Yes. Next slide. Okay. So, and I'll tell you why we do it for the muon and not. G-2. Okay, the two parameters are Me, the mass of the electron, and alpha, which is e squared by 4 pi in certain natural units, which are named in honor of Sommerfeld. It's called the Sommerfeld fine structure. Okay? And then this is included to all the others, and as I said in the Dirac equation, P is equal to 2. So the first measurements of the G-2 were done with the electron in atomic systems. The reason why we do it with muons today is that this is more sensitive to higher order effects because of the mass of the muon is much larger than the mass of the electron. So this is a paper of Julian Schwinger. The entire paper is just from here to here. That's the end of the paper, by the way. It's not like I missed anything over here. So the key thing to look at is this number over here, which he gives. Today we write it as alpha by 2 pi. Somebody quickly estimate it for me. Alpha is equal to? Please divide it by 2 pi and take out. No, don't take out your computers. Do it in your head. Yeah. 2 pi is roughly 6.3 times 137. Roughly, yes. Right. So that is the number that he gives over here, which is 0.001162. Okay. So Schwinger did this calculation. It was the first calculation of such a quantity, and it turns out that it is finite, and you don't have to go through all the procedure of normalization and regularization that is often necessary in quantum theory. This is one instance where it can be computed finite thing. But you see, he was doing it at a time when nobody knew the theory. He was just doing it off the bat, And this was, let's see, which year was this? 1947. So good to keep in mind, 2 years before that was the end of the Second World War. And during the war, what were people like Schwinger doing? Very brilliant students. At the war, what were they all doing? Not him. He was asked to come for the Manhattan Project, but being a physicist or whatever, a very private person, he didn't say. He instead went for the radar project, which is at MIT, and at the end of his work, the radar project, he was the world's greatest experiment, an expert on beam functions, and so, but he must have been doing this on the side, and he worked out his answer. So, there were 2 Nobel Prizes soon afterwards, one for something known as the lamp shift. How many of you here heard of the lamp shift? All of you have heard of the lamp shift. So, it is a splitting of 2 of the lines in the hydrogen atom spectrum, which is sub-leading to fine structure that was measured by Willis lamp, and it is an example of denormalization. So that Nobel Prize of Willis lamp was shared with Polycarp Push. Over here is the author of this paper, and as my young friend over here who liked me needs a haircut. So this was in 1948. So he measured the magnetic moment of the electron. Okay? So he did that with the electron in an atomic physics system. He didn't do it with all these rings and particles decaying and all that. And let's see what's the number he gets over here. He gets 119 plus minus 405. You see, 1948. You can imagine what kind of instruments they must have had. They have spectrometers and stuff. But he's right there on the board. So if you are to find a very nice formula that is as elegant as what Schwinger did, it may actually be engraved on your Grabstein or your gravestone. But anyway, so this 1918 to 1994, as you see, so he's a fairly contemporary person. So his gravestone carries a formula for making pi. Someone else's carries logarithm or something like that. You know? Okay. So this was at leading order in quantum electrodynamics. So then what happens at higher orders? So that is really the holy grail in this business, to compute it at much higher orders and to compare it with experiment. Okay. So here it is. So this is what we did. And it essentially arises because of activity in the vacuum, which is sensitive. So if you find a mismatch between theory and experiment, and you think you've done both equally well, that means that the mismatch must be accounted for by other activities in the vacuum that is not described by known interactions. Okay? So any mismatch here would be a signal of interactions not described by what we consider as the theory of quantum physics. So one way of doing this is to take the interactions and solve them on a computer, and this goes under the name of lattice gate theory. The lattice, as you know, is like a window, but this is a lattice where you discretize space-time on which you do computations. It's a very sophisticated system. It's already about 50 years old, with very powerful supercomputers with tons of memory and fantastic clock speed and distributed computing in the cloud and every possible word that you can think of, except that so far I've not heard AI and ML in this context. So these are the experimental results as we knew them. So let's see, the top line over here is Brookhaven, and then you have the various Fermilab experiments over here. So the first one was reported in 2021, which is called round 1. Then later there's run 2 and 3, and then eventually runs 4, 5, and 6. And what you see over here is the number of muons collected by the muon g-2 experiment. What's a decent number with it? Number of muons you would like to collect, and then you send an email to your dad saying, very proud of the number of muons I collected today. How many would you like to collect? 200, 2,000? This guy is very modest. This is, I think, about, what is it, 300 billion? 300 billion. I think billion as in 10 to the power of 9. So you see also the growth in the number of events. The very first round 1 was a small number, and then it increased, and then along the axis also you have the time. These experiments ran for longer periods of time, and then total number of muons that were studied was 300 billion. Okay? That's a large number. And that's the reason why you have continuous improvement of the measurement, because it brings down the statistical error, which, as you all know, goes a square root of n, 1 by square root. So these are the theoretical predictions over here that we have. So this pink band is the experimental finding, whereas all these other scattered results shown over here are the various theoretical computations of the g-2. And what is shown over here is the differences between the standard model and the experiment multiplied by 10 to the power of 10. Why 10 to the power of 10? Because this is now measured up to 10 decimal places. Listen to that amazing thing. I said 0.00116 or something like this, right? 1 by 180. It was hardly 2 or 3 decimal places. It's now to 10 decimal places. Which means that the theory also should allow you to compute this thing to 10 decimal places. That's the amazing thing. And a lot of these things is coming not from quantum electrodynamics, but from the presence of strongly interacting particles in the vacuum.
Why is there an error bar in the prototype?
Because this so-called theory also requires the modeling of these effects coming from the vacuum using experimental information which have errors. And my own work is associated with trying to reduce some of these errors using a variety of techniques. It's not easy because a large number of experiments performed over a long period of time in E plus E minus colliders, Italian experiments, then there was also Japanese experiment, American experiment, Russian experiments, most recently Chinese experiments, each of which has their own way of trying to figure out what these contributions are. There are well-known formula which allow you to relate the production of particles in this blob to evaluating their contributions to the g-2. Okay, so this is where we are, and this is where we were some time ago. I think this is an older one where you had the so-called standard model prediction over here, Brookhaven over here, Fermilab. Now you see, this is at the time of the run 1, that Brookhaven, which was done at the end of last century, and this was just done about 4 years ago, they're in essential agreement. Now these are the things that we have to think about and marvel that these experiments done over, 2 decades apart. Of course, it's the same magnet. The magnet has been transported, the electronics has been changed, the detectors have been changed, etc., and still the answer is so stable. Okay? So this again gives you the various ways of estimating these theoretical contributions, and I like this little logo over here, the spinning Muon. Okay? So this is the final answer which came from Brookhaven. So this is what, so multiplied by 10 to the power of 10, you have this number over here. These are the uncertainties times 10 to the power of minus 2. Okay? So you can see that this thing is changing all the time. And the precision of this experiment is 139 parts per billion. And you can imagine what kind of incredible precision that is. These are the various publications that you can look at. So I'll just give you some representative corrections. This is the simplest calculation. This is the one that was done by Schwinger. Now today we have other particles that we know that come from the weak interactions. The Z, we know about the Higgs, various other particles over here. This is what is called light by light scattering. Okay? 2 photons producing 2 photons. This is very strange because we think that a photon doesn't interact with itself, which is true. Classically it doesn't, but you can produce particles in the vacuum, various E plus E minus pairs which can then radiate somewhere and so on. So that scattering actually was first studied by someone called Delbruck. If you heard of Delbruck, it's called Delbruck scattering. Now Delbruck did the scattering and then he got fed up with particle physics and went to biology and then won a Nobel Prize. So here's a sample of QED diagrams. Now this is not random doodling, okay? So there are fixed rules which are known as Feynman rules, which tell you exactly how to draw a diagram. You have to draw all possible diagrams, and associated with every diagram, there is a number that you evaluate, which is known as the Feynman integral. Okay? Because there are integrals where you do an integration over virtual momentum circulating in the loop. Okay? So, for every diagram, there's an integral which has to be evaluated using procedures that we call regularization and renormalization. So here's an example of really fantastic. So these things here are, for instance, what does this remind you of? Does this remind you of something? This one here. Rainbow. They are called rainbow graphs. So this is what I told you. So this Brookhaven is here, and here's Fermilab, and this is all this thing. And this is the ring that you see over here. And the decaying muon will produce a particle whose energy will be less than that of the muon, right? Why does it have to be less than that of the muon? Because there are two other daughters which are also carrying away the momentum. Therefore, it will have less momentum. And because it has less momentum, where should it go? It should go into the interior of this ring, because it will curl into the magnetic field and go in. And so, you see, again, basic physics principle, you put detectors over here, so that the daughter of the decaying muon will hit one of the detectors. That's a simple principle. So this thing over here, I think I'm exceeding my time by a factor of 2. But anyway, so I'll be done in about 10 minutes. Okay? So these are the various features of the decay over here, and it's the same thing that was used both in Brookhaven and this. Okay? So here are all the various properties of the muon that I've given you here, and this is the precession frequency, which obviously has to have a piece that is proportional to the magnetic field, the strength of the magnetic field. The larger the strength of the magnetic field, the stronger will be the precession, right? So the frequency will increase. Then there's one more term, which is this thing over here, which is a cross product of the velocity with the electric field. The electric fields that are used to focus this beam, make sure that it doesn't wander away. However, this comes with a beautiful pre-factor, a mu minus 1 by gamma squared minus 1. This gamma is a combination of the velocity divided by square root of 1 minus velocity squared. Okay? So, if you look at this and I ask you, how can you make this thing vanish, the second term? You can tune the velocity of the gamma so that this a mu is equal to this expression inside the parenthesis. And that's exactly what is done, because you already know a mu. You may not know it to 200 decimal places, but you already know it to enough decimal places so as to make this contribution vanish. So that's the astonishing thing, that you tune the energy of the incoming muons to this quantity that's known as the magic energy to make this contribution vanish. Again, these are all the principles that go into what we are doing. Okay. Supposing you are a lighthouse. No, you're not a lighthouse. You're watching a ship coming towards you. Okay? And then there is, let us say, some kind of a rocket that you launched from there, and then the rocket is going to come towards you. Anyway, the ship is coming towards you, and this rocket over here is launched, and supposing the rocket is in the same direction as the ship that is coming towards you, will it come quicker or will it go faster? Or will it take longer to reach you? I'm asking you a simple question over here, because that's the principle that we have over here, right? Here is this thing, this precession vector is going to do this, and then the particle is decaying and producing a cone of particles in the forward direction. But of course, your detector is sitting over here. Eventually, of course, it will reach you because this particle is boosted towards you. So it does matter where this thing was pointing, because the energetic particles are coordinated in this direction. So, if this thing is pointing away from you, it will take longer to reach you, and if it is pointing towards you, the boost is also in the same direction, so it come towards you. Supposing there is no such vector and this particle is just coming towards you, what is the law for the arrival time that you have from a decaying beam of particles? The same radioactive law over here. And then if you had a log plot, how would it look? If you had a log plot, it would be a straight line. So now you have this effect of this thing which is spinning around, and whether the shower of particles was emitted in the direction where you are sitting, or they emitted at some angle, or whatever. So what do you expect to see in this log plot of the straight line? What do you expect to see?
Have a vertical loop
Not a bit, but it will have a modulation as this thing is going around.
because of the uniform magnetic.
So it will have a modulation. I'm just trying to give you a heuristic picture. There's a theory behind this, and you'll have to work out all the expressions. But loosely speaking, this is the idea, okay? That you have a bunch of crackers that are going off on the ship, and it depends on whether the ship, that cracker, let's say, is on a trolley, and the trolley is moving around on that ship, and the ship is moving towards you, and then these crackers are coming towards you or going away from you. At the time that cracker explodes, okay? And we're all used to Diwali crackers, so it shouldn't really come as a surprise to us that we see that. So on the log plot, if there was no precession, it would be a straight line, and because there is a precession, you're expecting to see a word that I'm looking for, a modulation, right? And the name of such a plot which has all this modulation is a wiggle plot. Okay, so this is what is called a wiggle plot. And what's the frequency that you see of this over there? It's the precession frequency. See, sorry, I'm getting carried away over here. It's not even my thing. Okay, good. So all these things we put together, and then we work out, and then let's see what the answer looks like, and then we fit the wiggle plot to various parameters, and from that we will pull out the g-2. So here is a wiggle plot over here. It's a really beautiful wiggle plot. What we have on the y-axis is the number of events divided by 149.2 nanosecond. It's the time it takes for a beam to go once around. This is the time after injection, modulo 102 microseconds. Now this is a really remarkable plot, because supposing you wanted over 7 orders of magnitude to plot this little plot, then I would need a really large scheme like that. Okay? But they have done it in such a beautiful way that this thing over here ends, and then it wraps back over here, and then over here. You see where this thing ends is where this thing starts. It's an extremely clever way of representing the data. This kind of thing you may see on seismographs also. You know, there will be a drum which is rolling on which you see this kind of thing. So, whenever they are doing these experiments, incredible amount of ingenuity that goes into all these things. That's the point that I'm trying to say. And the main source of uncertainty theoretically is what is called hadronic vacuum polarization contributions. Hadrons are particles that interact strongly, and in QED it's easy, but at least possible to compute precisely, whereas the others, as Aman here was asking, why are those uncertainties there? It's because of the modeling of this data and the problem. Okay? So these are the kinds of things that go into understanding this g-2 experiment, and I think my work has to do also with evaluating some of these uncertainties. I don't really have time to talk about this. It's the use of many different things, ideas that we have come across, such as the optical theorem. Optical theorem is a very generic principle in quantum mechanics. It has to do with probability conservation, and to be able to relate these particles about which you don't know much, and to milk out its contributions to the g-2. I can't go into all these things. Let me just skip this and then tell you that this is the kind of work that we have done. And our work is also reported over here. ACD over here is myself, Kapeni and Das. These are my 2 long-term collaborators. We have estimated some of these uncertainties. These are various other groups. We also show up in yours slides very soon. So I think I should skip all this, and I better be much more systematic next week when I'm talking about these things. So I'll stop over here and say that, you know, there's a very detailed procedure by which you can extract these theoretical contributions. And today there is still a mismatch between some of the theory and the experiment. about which you are going to tell us.
Is that intelligible?
Can you hear me? Yes? Okay. Right. Okay, so you're all undergrads, right? So you still have a lot of time to decide what exactly you want to do. Who of you wants to become an experimentalist? Okay, let's say you guys are just forming a group and you're in your basement, you're building a detector according to what Alan already described in his talk before. So what we want to do now is we want to see how we can really improve such an experiment. For example, these people at Fermilab or Brookhaven, they've done an experiment in a certain way, and now we need to discuss how we can really improve such an experiment so that we are able to measure this quantity, which is the anomalous magnetic moment premium, to such a high degree of precision like they actually did. Okay, here's a short or small cartoon on what actually happens in this ring. There's the muon, and under the influence of the magnetic field, it will start to precess while it revolves around the ring. So don't drink and drive. Okay. So in order to measure the magnetic moment, we actually have to take care of several things. The most obvious thing is probably the magnetic field that we need, and also the characterization of it. Because if you don't really know the magnetic field in which the muon evolves, then you cannot measure anything because you don't know what is actually happening. Of course, you also need to make sure that you can properly track the decay products, because if you want to measure in which direction the muon spin points, like using the asymmetry, you will know that the decay of the muon will be, or the decay products will be dominantly into the direction of that spin. So you need to track the particles, and maybe you also want to know the energy. Why exactly you want to know the energy, we will come to that in one of the later slides. And of course, there are various other things. You need to make sure that you inject your muon beam properly into that storage ring, and you need to properly confine it in the vertical and horizontal axis, which is why we need some more electric field contributions. And there are lots of things that are entering these uncertainties that you essentially get, and we want to minimize them. And in the end, or in the last part of my talk, we will also briefly talk about the hadronic reactive polarizations and about the theoretical status, or the status of the theoretical predictions. Okay, let's again look at this formula that you have already seen in the first part of the talk. So, of course, we already know that this precession frequency depends on the electric field, it will depend on the magnetic field, and it will depend on the momentum of the particle. The momentum is chosen in a clever way such that the dependence of the electric field will be gone. So, if you have some not ideal characterization or not ideal measurement of the electric field, you don't have to be completely, you can, by choosing this momentum, you can at least partly ignore these things. I say only partly because it will still depend on how you inject all of these particles in the ring, but we will talk to that later as well. Okay, so we now know that the electric field doesn't contribute that much, but still we need to characterize the magnetic field. And how do we do this? That's essentially the question we have to answer now. For this, let's first look at a cross-section of these magnets that they're using. So you see that muon region where there's a plus. This is essentially the beam pipe. So this is the cross-section of the beam pipe. The beam would come out of this, out of the plane, and the magnetic field would point vertically in this. So meaning that the beam pipe comes out. It's a ring. So at some point it goes back, and if the magnetic field points upwards, then by having a momentum inside that plane, like into this plane, you will be able to make your muons revolve in a ring. And of course, because it has a magnetic moment, it will also start to precess in this plane. Okay, what you also see is that there are some probes. These are, in this case, N and R probes that are supposed to measure the magnetic field that is present inside the chamber, inside the storage area. And this is exactly what we are going to talk
talk about now. So these fixed probes are essentially one part of 3 of this magnetometer system. So these fixed probes are, there are 378 NMR probes that are distributed in the ring at fixed positions. And these are able to measure the magnetic field during the runtime. So if there's a vacuum inside this ring and there are muons inside, while these muons are revolving, you can live measure the magnetic field. That's of course a great thing, and you need that because if you want to measure, if you want to essentially correlate the direction of the decay products to an actual magnetic moment, you need to know the magnetic field at the time of the decay. Alright. Of course, there needs to be some way to calibrate all these probes, right? If you have some probes in this ring, how do you know that they actually, that the values that you read off in there are actually correct? Okay, you need some kind of calibration system, and this is being done by having one calibrated probe that you check against. And the third part is a so-called trolley system, meaning that in this ring there is a small garage somewhere, and in this garage there is a trolley. And this trolley can be pulled through that ring, essentially with a cable. So, every 3 to 5 days they will do this. They will pull this trolley through the ring, and on this trolley there are 17 NMR probes. And these 17 probes, and because that trolley is essentially movable, you can map out the field in this ring. So, for all angles, you can essentially offer for some number of angles that you choose, you can measure with these 17 probes a cross-section in that ring, and then you average over everything, and then you get a magnetic field distribution inside, like an average distribution inside the ring. But of course, because the trolley blocks the beam, this is only possible if the beam is switched off. And so this cannot be continuously done. Okay, so now the question is, why do they choose to use NMR probes? Does anyone know why they choose NMR and not, for example, the Hall effect? Maybe the Hall effect is much easier to read out because everything is electronically. Well, the reason is essentially because the magnetic moment of several materials can be measured to extreme precision. And if you have a lot of particles with that moment, then you can get a large signal out of this measurement. For example, the gyromagnetic ratio of the proton is measured with a relative uncertainty of 10 to the minus 10. That is good enough, at least, to do this measurement. And if you can measure the gyromagnetic ratio for a certain material with such a great precision, then you know exactly, or to a good accuracy at least, how the Larmor precession frequency of this material is related to the magnetic field. Because this gyromagnetic ratio is really just the prefactor of this relation. And of course, we need to choose a material that produces a Larmor frequency that is easily measurable. So the proton itself will be a good candidate because, I mean, you see the gamma p comes with the 1 over the mass of the particle. So if you take the proton for this and you plug in the proton mass, then you will see that with reasonable magnetic fields, about 1 Tesla or whatever, you will get some 10 megahertz of Larmor precession frequency, and this is electronically easily measurable. On the other hand, if you plug in, for example, the electron mass, then you're already 4 orders of magnitude larger, so this will be much more difficult to measure. So the proton would be a good candidate. And of course, then you can ask, what materials do we know that have a lot of, or that have a high proton density, and still a well-characterized gyromagnetic ratio. And the first material that probably most of you would guess is water. The first material that comes to mind would probably be water, because it's so abundant, it's easy to purify and easy to work with, right? And indeed, the gyromagnetic ratio between water and the pure proton is actually almost 1. I mean, it doesn't have to be 1 because we can just measure this, and this can also be measured to great precision. You just have to make sure that you purify your sample enough before. And because it's so easy to work with water, this is actually the material that they use for the calibration probe. And NMR measurements are, because of all these reasons, are quite precise, so you can achieve an order of 10 parts per billion of accuracy with these measurements for your magnetic. Okay, so while they are using water for the calibration probe, this is not the material of choice for the fixed probes and the trolley probes. So, I mean, once you can cross-check them with some good calibration probe, then you don't need to have a very, very well characterized material anymore. Then it's more about what kind of material can you find that gives you a large signal, so that you can minimize your measurement uncertainties by measuring this precession frequency. And there are lots of materials which have a very high proton density, and the material that the people at Fermilab choose here is a certain type of petroleum jelly. And I think it's not a standard one that you can buy, it's a specifically engineered one, but yeah, this is the material of choice that they have used in the fixed probes and the trolley probes that are actually mapping out the field inside that storage. Okay. And of course, these need to be cross-checked with a water-based probe, and the water-based probe itself is also cross-checked against the helium-3 probe, because helium-3 is, yeah, you can build very precise calibration probes with helium-3, but I think they need to be cooled so such that you don't have to build all this kind of infrastructure. You just cross-check it with this and calibrate this, and then use the movable water calibration probe in your actual experiment.
Why it gives us larger signals than the water?
Yes, the reason for this is that in a certain volume you have a much higher, or the proton density that you have in petroleum jelly is much higher than in water. I mean, petroleum jellies are essentially some type of wax, right? So in these types of wax, they are made of a lot of hydrogens and a lot of carbons, and water is just, well, 2 hydrogens and 1 oxygen. And the materials are just made in this way that the density of protons is higher. This is the reason why we have a higher signal with these petroleum jellies. Okay, so the fixed probes are located at 72 angles in the ring, which is fine, okay, but you can't really map out the field. Also, at each of these 72 stations, you have either, I think, 4 or 6 NMR probes, and this is, of course, much less compared to the 17 probes on that movable trolley. And this movable trolley that they pull through the ring every 3 to 5 days to map out the complete field distribution, they can do this, or they choose to do this with more than 8,000 angle positions in that ring. So they can really get a quite precise idea or a precise picture of how the field distribution really looks like in that storage ring. Okay. And the reason why they redo these measurements is because you may have some drift. Right, you have over time maybe you have a temperature change, or over time maybe your petroleum jellies start to degrade. I mean, they degrade quite slowly, which is also one reason why they choose them as the active sample, right? But maybe there is something going on, so maybe over a few weeks or even just days, you might have a drift in signals, or maybe a drift in the field distribution itself. So this is the reason why they synchronize these fixed probe measurements with the trolley measurements to get to take into account the drift of all these drift effects. And one thing that you have to take care of while doing that in your basement experiment is that while you do this measurement, well, the trolley is made of a material, you have wires and so on, so the trolley itself, just by being present, will distort the field. So you just have to make sure that while your trolley is close to one of the fixed probe stations, you should not take these values that you measure there for granted, right? So you have to actually switch that measurement off and interpolate between the next ones. And then you use the trolley measurement as some data that you have to perform this interpolation. Alright, so, yes?
So will the trolley affect the trolley probe itself?
So that I don't know. Probably there are some effects, but I think they take this into account in some kind of as a systematic uncertainty. But I think I hope the trolley is designed in a way to kind of minimize this, and I think they are aware of this. Okay, so now we know that with this with this trolley we can map out the field, and then of course the natural question is how many field maps do we actually need to perform the measurement? In run 1, they chose to use 16 field maps. Okay. In run 2 and 3, they already increased that number to 69. and after run 4, 5, and 6, they had a total of 194 magnetic field maps in total that they were able to use to carry out the data analysis. And from the number of field maps in run 2 and 3, they were getting an uncertainty of about 38 parts per billion. And just by using the greater number of field maps, they were able to reduce this uncertainty to 30 parts per billion. And of course, these are just the uncertainties in the cross section. And if you go along that ring in the azimuthal direction, you will also have some uncertainties. These are about like smaller than 20 parts per million. Note that this is a million and not a billion. So this is, of course, several orders of magnitude difference. But does that destroy the measurement? That we don't know that well in the azimuthal direction? No, not really, because the variations are expected to be much smaller than the distance that the muon travels before it revolves. So what the muon actually sees is some kind of average, some angular average. That's the reason why this 20 parts per million are not that big of a deal. Okay, so here you actually can see the muon distribution, which is the color graded part, together with the deviation of the magnetic field from an ideal homogeneous field. So before you know the magnetic field is pointing in this direction, right? So you have some kind of muon region, and in this region you want the magnetic field to be as homogeneous as possible. And you see that they can really achieve this to kind of an impressive accuracy, because almost at all places where muons are present, you have almost no deviation to the ideal homogeneous field, which are exactly these 0.0 lines. Alright. Okay, so let's talk a bit about the beam and how to track the decay products. So the beam itself is not a continuous beam, it's a pulse beam. So whenever there's an injection of muons into that salt ring, that injection time lasts about 120 nanoseconds. So the beam has some temporal width of 120 nanoseconds, and this time is chosen such that almost all of the ring is actually filled. It's not the complete ring that's filled, because you also have some kind of dispersion in that as well, but almost all of the ring will be filled after this 120 nanoseconds of injection time, when you inject muons with the magic momentum. And the muons are stored for 700 microseconds, and during these 700 microseconds you let the muons, or the muons will decay, and you record the decay products.
First number the nanosecond.
Yes, the 700 microseconds will be several times the lifetime of the muon in the lab frame, which is larger than the 2 microseconds of rest frame decay. Alright. Yeah, so we already saw this kind of muon distribution. So how do they actually measure that? Does anyone have an idea?
Using where the decay products are.
Yes, exactly. You measure this from the decay products. So suppose you have a muon on the ring, the muon decays, and if you are able to track that curve, you can extrapolate it back to the decay point, and then you just mark this as a muon was there. And if you do this with many muons or with many events, then you get these kind of images. Then you get images like these, so you can actually track the full muon distribution. Of course, this is an angular average, an azimuthal average that you see. Okay, and in order to properly carry out this extrapolation back to the decay point, once you have this tracking curve, you need to precisely know the magnetic field, because the particle path will depend on that magnetic field, and if you don't know the magnetic field, then you have no clue how to use that tracking information to go beyond the part or back into the ring where you don't have this tracking curve available. And this is the reason why these precise magnetic field measurements are actually so relevant. And yeah, by improving the magnetic field measurements by just using more maps, they were able to reduce or cut the tracking uncertainty essentially in half, which is also quite impressive because these uncertainties are uncorrelated, so you have geometric addition under the square root, right? So it's kind of impressive that they are able to cut this in half just by improving the measurement of the magnetic field. Okay, so the storage ring that they used in Brookhaven and Fermilab comes with 24 stations at which you have tracking combined with energy measurements of the decay products. So these are straw tracking systems. Does anyone, or do you know how straw trackers work or what they are? Or have you heard of this phrase, straw tracker? Essentially, what you have is you have tubes, and in these tubes you have a gas and a very thin wire. And then you apply a high voltage to that wire, and if a charged particle travels close to that wire, then you can then you ionize that gas and you measure a current, essentially. And so whenever you measure a current in one of these tubes, then you know a particle is going through this. And this way you can, if you have many of these, you can track where the particle is essentially going. These are pretty standard tracking types of trackers. They are also used in many experiments at CERN, for example at CMS and Atlas. So you may find these types of trackers in many experiments. And the calorimeter, which is the energy measurement, this is done in some type of crystal. In this case, it's a lead fluoride crystal. And there they use the so-called Cherenkov effect. Have you heard of the Cherenkov effect? Yes.
Have a long line that anything is going faster than C by E.
Yes. Exactly. So suppose you have some volume, and in that volume, because it's a material, the speed of light in that material is smaller than the vacuum speed of light. And if you have a particle traveling faster than that speed in this medium, you will see a cone of light being emitted. And this can be used to estimate the velocity of the particles, and if you know the mass, then of course you also know the energy. So this is how you can measure the energy. You just need to detect this type of light, and this light detection is done by so-called silicon photomultipliers, which just take this light, convert it into a current that you can measure, and then you know how much energy was actually deposited into that material. And the reason why you need to know this type of energy is because you want to use the asymmetry in the decay properly. So only the very high energy particles will actually be mostly emitted in the spin direction of the muon, and the low energy particles can also or have a higher likelihood of being emitted in other directions. So this is why these analysis groups, there are 5 analysis groups, there are 5 groups of people who are actually performing the analysis of the data that they collect here. They use a so-called energy cut. And energy cut means whenever you detect an event, like you measure the decay product, and that decay, like that positron that you have had an energy higher than 1 GeV, then you will use it in the analysis. If you don't do that, you will wash out the wiggle plot a bit, and the data analysis will be much harder to perform. Okay, so here's a schematic of how these tracking things actually work. So this is how the tracking stations look like. You have your ideal particle path. Then a decay product will have less momentum or less energy than the muon which decays. So it falls into the ring, and on the inside. It moves through the trackers, and eventually the energy will be deposited in the calorimeter, and this tracking information can be used to find the exact point where the muon decay. Okay, so now we know that if you characterize the magnetic field well, and if you perform all these tracking things properly, then you can have a good idea of how the muon distribution looks like and so on, and you get this nice wiggle plot. But there are also other sources of uncertainties present. For example, how do we make sure that we actually only have muons in the ring? Because we already know the muons are created by, first you have protons, you shoot protons on a fixed target, you create pions, and then you use the decay products of the pions, which are the muons, and you inject these into the ring. So how do you make sure that you don't inject some protons or some pions into the storage ring as well? Well, of course, experimentalists are smart. They try to minimize those effects, but they cannot completely prevent other particles from actually entering the ring. And these particles, these protons and pions, will also create signatures in the detector. And these signatures are called the hadronic flash. And the hadronic flash has essentially 2 parts or 2 components. One component, which is called the prompt component, is actual protons or pions entering the calorimeter. So you measure directly their energy deposition into the calorimeter in your photomultipliers. And there's also a so-called delayed component, which is essentially coming from neutron capture. So what you have is, you have, for example, a proton entering the storage ring and hitting the surrounding material, like hitting the walls of the vacuum chamber, for example. And then what you do is, because these protons have a lot of energy, you can create neutrons. And these neutrons may be captured by the surrounding material, and in this neutron capture process, you emit gamma rays. And the gamma rays, of course, you can also detect with your photomultipliers, because the photomultipliers, they are trying to detect photons in the first place. And whenever this happens, whenever you have such a measurement or such an event, it actually doesn't matter if it's an event from the hadronic flash or an actual Muon event. What you do is you measure a current, and in your photomultiplier or in the electronics, you have to replenish the electrons or replenish the charges before you can actually record another event, before another signal in the current can actually be triggered. And this is due to because all your electronics eventually will have capacitances, right? So once you deplete all the charges, because you have a capacitance, it takes some time to get the charges back up. And if too many events are coming too close together, that means that one event depletes the charges, you record that event and below the energy, but when the next event comes, maybe the charges have not been completely replenished, so you don't really get a true picture of what's going on. And this means that if you have too much of the hadronic flash, these things happen all the time. And what happens then is that you have a reduced gain. So you measure less signal than you actually would measure if you wouldn't have the hadronic flash. And you have to somehow account for this, because otherwise you don't know how much energy the particles actually have. And you might have to discard more of the events than because you underestimate the energy. So all of these things are very important in order to get the uncertainty of the measurements low, like to get to better statistics or to record more events. And this is actually possible to account for. And how these people are doing this is by utilizing a laser-based calibration system. So what they are doing is, they have a reference laser, they exactly know the wavelength and the intensity of the reference laser. So they just have this laser and they shine it onto the PMTs. They know which signal to expect, and if the gain is reduced, they can, in a post-processing step, correct for this. So if for example, the gain is cut in half, right, then you see this with this reference laser, then the reference signal will also be cut in half. So you know everything you record has to be multiplied by a factor of 2. So this is how you can account for such addition for uncertainties that are coming from this additional injection of protons or pions. Okay, how do we make sure that the beam, once it is injected, okay, let's say we only have muons, let's say we don't have protons or pions, let's say you have a muon beam, you inject it into the ring, right? You have the magnetic field, so you know it will be in a circular motion, right? How do you know that this beam will actually stay a beam and not, because the magnetic field will perform some refocusing horizontally, right? Because they're in the plane of the ring. How do you know that it doesn't drive apart in this way? Because the particles are charged, right? So they should interact and they should repel each other. But if you don't account for these kind of effects, this is actually what would happen. So you would disperse your beam and you would lose a lot of muons. So you have to make sure that this doesn't happen. And in the Fermilab experiment, they did this by using a quadrupole field. So the field distribution looks like this. So this is also a cross section of the beam pipe again. You see that the field lines of this quadrupole are pointing towards the center in the vertical direction, right? So this can actually perform some kind of vertical focusing. Of course, it drives it apart horizontally, but you already have a horizontal focusing effect from the magnetic field itself. So if this is a properly adjusted field, you won't disperse it in the horizontal direction, but actually have a proper confined beam. Okay, so this electrostatic quadrupole system has been changed throughout these experiments. For example, in run 1, 2, and 3, they just had the static field. That is also why it is of course called electrostatic quadrupole. But in runs 4, 5, and 6, they did some changes to it. And what they did is they added the opportunity to modulate these electric fields with radio frequencies. So they have some radio frequency modulations of this. And why is this important? This is important because even though you try to inject only muons, you are not really sure that you inject them properly. So because of all these fields that you have inside your beam pipe, you know that there's a certain allowed phase space for which the particles are actually traveling along a ring, right? So if you don't match this phase space, if your injection doesn't really match the proper injection position and injection momentum, then this whole beam will start to oscillate. And this is what you call coherent Peterson oscillations. Essentially, you can think of it, instead of going on a circle, there will be an additional kind of wobble that you have. And this wobble can, of course, also happen vertically. And because you have these kind of oscillations, you need to somehow try to get them under control. And this is what they essentially did with this upgrade to the ESQ system. So these radio frequencies that you use or that you modulate on top are supposed to suppress the formation of these coherent Peterson oscillations in the first 6 microseconds after injection of the beam. Okay, and of course there are reasons for why these coherent Peterson. Yes?
So you are modulating the electric field with the RF signal, right?
Yes. So this field will be modulated by several.
That will change the magnetic field too, because the electric field is not changing with time. So the new magnetic field can also alter the motion of the particles.
Yes, but at these frequencies, I mean, if you have an electric field and a magnetic field, due to the time change, I think if you look at Maxwell's equations, the magnetic field should be quite small and suppressed by 1 over speed of light or something. I'm not entirely sure, but I think if you take the plane wave ansatz, you will see that one of them is suppressed by 1 over c. So this will be small compared to the magnetic fields that you have in there at these frequencies. Yeah. Alright, so the reason for why you have these oscillations, for why you don't really have the exact phase space is, of course, because first of all, not all muons have the same momentum, you have some momentum distribution. And second, when you inject the muons, there is a so-called kicker magnet that is supposed to bring them on the proper path. But since you have not only muons in one particular point, but a distribution, if you do that ideally, then you will see that you will lose a lot of muons because they are not, they are kicked too much. So they will hit the surrounding walls, so the muons are lost and you can't use them in the experiment. So what they do instead is they underkick, they don't have the proper phase space match, meaning you get these oscillations, but at least you have more muons in your muon. And if you don't account for these Peterson oscillations using such an RF system, which essentially happened in the first 3 runs, you get a 0.8 ppm shift in the measured frequency, in the anomalous precession frequency. And if you, like with the new RF system, they were able to reduce this uncertainty by a factor of 8, which is also quite impressive. Like a factor of 8 in uncertainty is kind of a big deal. Okay, yeah, and how this essentially works is that if you don't have these RF systems, then muons that have high momentum and are close to the ideal orbit, the ideal orbit being the exact orbit that you calculate from your synchrotron equations, then these high momentum muons are actually remaining close to that orbit, but the low momentum muons are pushed away. And the RF system essentially takes the low momentum muons and brings them closer to the ideal orbit and takes the high momentum muons and pushes them out. So what happens is that you rebalance the whole phase space, so the beam cross-section doesn't look exactly the same. Maybe it is slightly larger or smaller and shifted outwards, but at least you get rid of these oscillations. So that's the basic principle behind this. Okay, and essentially this RF system has been used in 3 out of 4 data sets, which you can see here. So the run 1, 2, and 3 of course didn't have that in the first place. And the first data set of run 4 also didn't have it, and then they employed several modes of this RF, meaning the RF signal can be modulate either the vertical or the horizontal plates of that quadrupole, right? So they had different modes of operation, and they used these in 3 of.
Before the RF, how were they doing it?
So before the RF, they had the beta oscillations, and they had to include them in the fit model. I mean, they have to do that still, but since they are larger, the uncertainty will be larger. So you have to account for this by a proper model of the beam. And all in all, if you try to do all these things we've talked about and even more, then you will see that the uncertainties will be in some parts of the experiment smaller than before, which is before meaning on 1, 2, and 3. Right? For example, you see the CE. The CE is exactly the uncertainty coming from the electric fields. They were able to reduce it from 32 parts per billion to 27 parts per billion. But, okay, other parts of the experiment are not that drastically reduced. Maybe the uncertainties in some parts are even larger. But the main point about these tables is that actually they collected many more events. So the upper part, the statistical uncertainty for this omega A and the superscript M stands for measure, this has been reduced from 201 parts per billion down to 114 parts per billion. So it's really a combination of all these improvements to the experiment together with much larger number of events that they actually measured. And I guess the number of events of the statistics actually plays a bigger role. Okay. Again, a comment on these beta tone oscillations. So what you see here is the wiggle plot, and the wiggle plot needs to be fitted because we need to extract the proper frequency. So you have a very elaborate fit model, and what you see is that the fit model needs to include all these types of oscillations. So these peaks that you see are on the y-axis, on the vertical axis, you see the residual of the Fourier transform of the residual of that fit. So if you don't account for all these oscillations of the beam, you see all these peaks. Right? All these peaks give you systematic errors because you didn't take something into account that you should have taken into account. And if you account for all these things and all the uncertainties or characterizations are optimized, for example, by reducing the CDO in the first place, you see that the residual or the Fourier transform of the residual with all these effects will not contain these peaks anymore. So you have a suppression of at least 3 orders of magnitude just by improving it in the fit model. So all these fit models that they are using, they are very elaborate. They contain a lot of parameters. I don't know how many exactly, but yeah, it's really a very elaborate thing to do. Alright, so there is, however, another type of uncertainty that needs to be taken into account, which is not of experimental nature, but more of a human nature. So if someone at Fermilab sits there and gets the data, he has to analyze the data, right? And the problem is that humans have this property that they are trying to look for patterns, for example, or maybe they are trying to look for things that they're actually expecting in the data. And this is what's called the researcher bias. So let's say some guy who's in this collaboration, he wants to analyze the data, but maybe he has read a theory paper before, and he has an expectation of driving the data, the experimental data, towards the standard model prediction, for example. Or maybe he doesn't like us theorists and he wants to drive it away. So you need to kind of account for such effects. And the way how they did this in Fermilab is by a blinding procedure. There are several things, or essentially there's one important thing that enters this measurement in a very crucial way, which is the time measurement. You're trying to measure frequencies, right? And you can only measure frequencies if you have a good time measurement. So what they're actually measuring is the ratio of the frequency in the wiggle plot to the frequency you have in the NMR plot, because they divide out like this, then divides out the magnetic field. And okay, so the wiggle plot comes from the calorimeter, right? So this calorimeter, or the electronics, they have a digitizer, and this digitizer runs with a clock. And the blinding procedure works now in the way that this exact digitization time rate is not exactly known to the analysts. So there's a secret offset applied to this. So the guys who get the data, they don't know what exactly the frequency of measurements actually was. And this is actually done for all the analysis groups, but relative to the analysis groups, each group applies a different software offset as well, just to not fall into the same traps that other groups might fall into. So just to distinguish the data. And only in the end, after all the data is collected, these offsets are made public, and then the analysis groups, which have developed the analysis tools, they plug in these values and they get the true value out of this. And then they cannot adjust it according to their expectations. So this is how you get rid of the researcher bias as well. Okay, these are essentially the main parts or the most important parts to drive the uncertainty to lower values, and also the main things that have been changed between 1, 2, 3 and 4, 5, 6. And here again, you've seen this figure already, now a bit larger so we can actually read it off. It's after the last one, they collected even more than 300 billions of positons, more than 300 billions of events, which is more than a factor of 3 larger than what they had after round 3. And this is really the main driver of the smaller uncertainty that we're getting. Okay. Are there any questions regarding the experiment?
Yes. I noticed that the Muon maps, magnetic field maps used in the later ones, is that because they've already accounted for magnetic field uncertainties using these figures?
So I think if you add up all these values, you should end up with 190 points. Anyone good at adding up things in their head? Or not?
I meant per one, not
Per run. I mean, look, after run 3, they had 60, 90 maps, right? And so after run 6, they had 194 maps, so they must have had more.
we take the total, it's not per.
So the total is small.
If you can show that the number of events plot, you can see what the
Yeah.
they're not the same number of events.
No, they're not the same. Yeah, they're not the same number of points. That's right.
I think we can skip the big one unless there is
Yes. I mean, what's the typical magnetic field strength of the magnetic field? Microtesla, right? So typically for these experiments, the magnets you use have order of Tesla fields. So there's a large separation of states.
this kind of backgrounds, they know how to count.
Also, like one uniform magnet, it's not really over 10 meters.
I think what's much larger are actually collimation effects and bending of field line effects due to metallic parts that you have. So I think to actually get the field homogeneous is much more difficult than accounting for such.
Easily shaded.
Probably. I mean, all these tubes must be metal anyway. Yeah.
In the slot tracking method, we ionize the particle. Like
This slot tracker. So in the slot tracker, you will have a particle that carries an electric charge traveling in a very strong electric field. And if this particle has enough energy to ionize that gas you have, then once it's ionized, that strong electric field has a kind of multiplying effect. Some charges being kicked out of some molecule, right? And then it's being accelerated, and once it hits the next molecule, it has enough energy to be ionizing itself. And this way you get some kind of avalanche effect.
okay, so since we are studying elementary particles here, or to be precise, muons here, how is the gas relevant for this?
I mean, the gas, a different type of molecule has a different type of ionization energy. So the molecule or gas you choose needs to be adapted to the experiment you perform.
And like, how are they related? I think.
What do you mean exactly?
Like how?
Asking the detection principles of the slot tracker. They have their own logic. Whenever an energy particle passes through the slot tracker, it has its own detection principle.
Yeah, so suppose you have a particle passing through that tracker. Once it ionizes some gas, you have a current flowing, because the electric field is driven by the wire and some kind of anode material, surrounding anode material, right? So the charges that the ionization charges will travel to these electrodes, and then they are measurable as some kind of spike in the current. So what you want to do is some kind of pulse measurement of currents. And whenever you have a pulse, you know there has been ionization event. And if this is correlated in many trackers, then you know this is actually not some random thing, but it's actually a path of a particle. Yes, but the ionization of energy of, for example, hydrogen is what? 13.6 electron volts. The energy cut is 1 beta electron volt. So it doesn't really matter.
How long does it take to, like, the minimum time between two measurements?
The minimum time between two measurements. You mean?
Even when the gas inside the sensor being ionized, so how long does it take to re-distribute that one?
I'm not sure. But what you have to take into account that there are so-called dead times. Once you have ionization, this whole thing also has some kind of time until it can detect another event. But I don't know how long these times actually are. But they must be somewhat similar to the dead times of the photomultiplier, because otherwise it doesn't make sense. Because you can only you only can measure or use the intensity of the energy anyway. So there must be some correlation between these two things. Okay, so do you have enough energy to go through the hadronic vacuum conversation a bit, or? Okay, I guess then we can also continue. It's really just a few slides anyway. So you've seen a plot similar to this, or maybe the same one already in the first part of the talk. What you see here are essentially theoretical predictions divided into two sets. So the blue arrow bars are lattice predictions. So these are lattice calculations that have been done. And the green ones are so-called data-driven methods. So the data-driven methods, here we see them in large. The data-driven methods essentially use some experimental input to estimate the contribution to the magnetic moment. And what you see here are several experiments, for example, SND, CND, Babar, Chloe, and all these. These are experiments from which the data has been taken. And for each experiment, there are three main estimates of how to use that data to produce a final value that has been analyzed or proposed by three theory groups. And they have some differences, some qualitative differences. So the point is that each of these experiments produces three predictions according to which prescription they actually follow.
Usually, each one of those three will be their own.
Yes,
Usually.
exactly. Yeah, that is correct. If you take one experiment and all these three values, you see that they are agreeing with each other. Okay, so this is a formula I cannot explain now. It has to do with the optical theorem that Ananthanarayan talked about before. The point is that the contribution to the magnetic moment of the muon depends on the so-called hadronic R ratio, which is essentially, as he already said in the first part, what you take is you take this blob in the final diagram, and then you take the production cross-section of E plus and minus to hadrons and a photon, or photons. And this cross-section via the optical theorem can be related to contribution in the magnetic moment. So I guess if you want to know more about this, you have to ask someone who works with these data-driven methods. I have no clue about this. But the point is that all these three values really are just, or the statement that there are three values is really just the statement that there are three different types of estimating this hadronic R ratio. So this is what's actually happening. And for example, the so-called KNTW method, which is called according to the names of the authors who came up with this, looks like this. At a certain center of mass energy, at a certain root S, you exactly have a prescription of which final states contribute in what way to this R ratio. So these are very complicated things. You can probably work a long time on such things. That's, I guess, why there are three main ways of doing that are being established, and not many more. And for the other two, I didn't really find such a nice plot. They only provide tables in the main publications. That's why I chose this to represent. Okay, let's go back to this plot. What do you see here? Is there something that you don't like about this? Or maybe something you very much like?
is the
Yes.
theory alone should be written.
Yes, so these all are theory predictions, right? But CMD3 is kind of off. All the others kind of agree, but CMD3 is off. Something else that bothers me about this is that down there you have CMD3, right? Up there with the other agreeing ones you have CMD2. So a newer version of that same experiment contradicts its own previous measurements. So this is of course a red flag. This is something you need to look at and something that needs explanation, right? And so essentially the statement of the CMD3 guys is, with our new measurement, there's almost no discrepancy between their theoretical prediction and the measurement anymore. But of course, all these other experiments that have been done decades ago, they are saying no, this is not true. Okay, so this needs to be understood, and maybe one way to understand why at least CMD3 contradicts its predecessor experiment.
What is the percentage?
The percentages, I think, refer to how much of this integral has been carried out, or something like this. I'm actually not sure. I think it's related to the integral, to how much of that integral has been carried out. Yeah. Okay. So, yeah, one possible explanation of why CMD3 is so different is, okay, maybe CMD3 got some upgrades. Maybe they changed the detector, maybe they changed the accelerator. Well, no, they didn't change the accelerator because CMD is at the same accelerator as SND. It's an accelerator in Novosibirsk in Russia. So the accelerator itself cannot be the reason. But CMD3 actually got some upgrades, some detector upgrades and electronic upgrades compared to CMD2. For example, they upgraded the drift channel. They have a completely new calorimeter and a completely new trigger system. And this, of course, could result in a disagreement with the previous measurement that they had in CMD2. But it doesn't really explain why it deviates from all the other experiments that have been performed as well. Why should all of them be much closer to CMD2? And yeah, this is essentially, as far as I know, still an open problem because the CMD3 collaboration didn't really make clear how they estimate the uncertainty. So there are certain correlations or uncertainties that carry an energy dependence, and the energy dependence is not quite clear in this analysis. And as far as I know, they have not yet given us a proper explanation for why that is. So the point is that if you look at this plot, maybe CMD3, until they give a proper analysis or a proper explanation for this, should be in some parentheses, should be bracketed out for now, and the discrepancy, at least in the data-driven methods, is still there. So this is...
In fact, in the last white paper, they say that they have no way of averaging over all this, and they say that we are only comparing the lattice. Stop. There will be a conference, I'm sure.
Yes, so there already was a conference where CMD3 people were present, and they had a special session where they have been asked a lot of questions. I think it was a list of more than 40 questions, and I guess we can expect an answer from them soon, several answers, I hope. All right, so this is essentially it. Now you know a bit more about how these experiments are actually performed, and also the current status of the theoretical predictions. Any questions?
Yes, so in what order of corrections do we take in lattice
Lattice? Yes.
It's not an order by order calculation. It's somehow supposed to be the whole thing.
So what they, how I understand, I'm not an expert on lattice, how I understand, what they do is they take the path integral and build a metropolis algorithm the same way or a very similar way how you would simulate the Ising model. Okay. I think it's also not important how they do it. It's, the point is it's non-compatible. Okay, if there are no more questions, I think then we are done.
I just want to give some closing remarks. Yeah.
Okay.
So, it was very nice for us to be invited by the graduate club as part of the thanks. We feel that as undergraduates, it's not just the subject that we're looking at, but also
learning how to approach a problem, how to talk about it, how to think about it, how to read about it, how to assimilate enormous amounts of information and to, give some kind of structure to this information overload. I think Leo's talk is particularly wonderful because, he's just closer to you all in age and to me. All of you are younger than my daughter, so what can I say? The way in which he approached and analyzed, and this is one of the things that you could use as an example for the studies. And he's going to be a theoretical physicist, but the freshness with which he read all these experimental papers, it shows that you can always try to be somehow a complete physicist. And today it's very complicated. You have to know data, you have computers, physics. So it's very non-trivial. So there's a well-known person, Tony Z, he's a very well-known physicist. He wrote somewhere, I think on Facebook, that he will be at least 40 by the time he will start to do anything in quantum physics. So don't get discouraged by all this, but just take a leaf out of this book. Thank you, Samuel. I don't know your name. Peter Bluto and everybody. Actually, of course, the word faithful as well. He was spinning on with his phone, and thank you all.
So thank you, sir and Leo, for the wonderful presentation. Yeah. Let's have a round of applause for them.